In our previous video, we looked at the definition of atmospheric stability and looked at the three main types of atmospheric stability that we can have in our atmosphere. As a quick review, recall that the moist adiabatic lapse rate, in other words, how quickly a parcel of air will cool if it is 100% saturated, is 6 degrees Celsius per kilometer. If the parcel is unsaturated, relative humidity less than 100%, then it will cool at a rate of 10 degrees Celsius per kilometer at the dry adiabatic lapse rate. Now we can tell the stability of our atmosphere if the environmental lapse rate, how quickly the atmosphere itself cools with altitude, is some number less than 6, then you are looking at an environmental lapse rate like the one I'm drawing right here. You have a completely stable atmosphere. No matter what happens, your atmosphere is warmer, the parcel is colder, the parcel will sink back down to the surface of the Earth. On the other hand, excuse me, if you have an environmental lapse rate that is greater than 10 degrees Celsius per kilometer, then it's going to cool more rapidly than any parcel would. So the parcel would remain warmer than the atmosphere. Parcel being more buoyant will then continue to rise. You are in an unstable atmosphere. The third option is right in the middle. If the environmental lapse rate is some number between 6 and 10, then it's what we call conditionally unstable. If the parcel is moist, then the parcel will be warmer than the environment. Well, so it'll cool at a slower rate, so it'll stay warmer longer. It'll be buoyant, and you'll have rising motion if it is a moist parcel. But if it's dry or unsaturated, then it's going to cool more quickly than the environment around it. And so it will be colder, and thus it will sink. Therefore, it is unstable if you're dealing with a moist parcel, stable if you're dealing with a dry parcel. Now, the dew point also drops with altitude at a rate of 2 degrees Celsius per kilometer. Let me show you what this indicates for us. Let's say that we have an environment where at the surface it is 25 degrees Celsius. At an altitude of 2 kilometers, the temperature drops to 12 degrees Celsius. That means there's a difference of 13 degrees Celsius, which cut in half means that the environment has a lapse rate of 6.5 degrees Celsius per kilometer. So we're dealing with an average situation. But now let's look at the dew point. So let's say that at the surface, we have a dew point of 16 degrees Celsius. Since it drops 2 degrees Celsius per kilometer, it drops down to 14 at 1 kilometer, then down to 12 at 2 kilometers. Well, if the temperature is 12 and the dew point is 12, then that means that the saturation vapor pressure and the actual vapor pressure are the same, which means that at this point, relative humidity is going to equal 100%. You are fully saturated. At this point, water starts condensing, and you start forming a cloud. This is the point where you will develop a cloud base. So let's say that, take our hypothetical situation again. We have a parcel of air at 30 degrees. The surface temperature is 30 degrees, dropping at a rate of, in this example, 9 degrees Celsius per kilometer. That's between 6 and 10, so we are conditionally unstable. A parcel of air, so the environment drops by 9 degrees also, so it drops down which cools at a rate of 10 degrees Celsius per kilometer, so it drops 20 up at 4 kilometers. Well, if the dew point temperature is 22 at the surface, then it drops at a rate of 2 degrees Celsius per kilometer, which means that it is now 20 degrees at an altitude of 1 kilometer. You are now fully saturated. It will start to condense and form a cloud. And then from there, since we are now saturated, we now cool not at the 10 degrees Celsius per kilometer that we did before, but 6 degrees Celsius per kilometer because it is now saturated air. It goes from 20 to 14 to 8. Now here's the hitch to this. Since the parcel is dry near the surface, it is under a stable condition. Notice at an altitude of 1 kilometer, your parcel is colder than the environment. But if you can get it to that point and go up a little further, now you are moist or saturated. That means that your parcel is going to cool slower than the environment, and there comes a point where the parcel becomes warmer than the environment and will freely move upwards. So if we can somehow get that parcel of air up to that point where it is warmer than the environment, physics will do the rest. The parcel will be more buoyant. It will just rise on its own. So this video is going to address the 4 main ways that we can take it from being at the surface, very stable condition, up to a point where we can freely convect upwards. Here are the 4 basic triggers to induce rising motion. So the first is convection. The sun heats the ground, and then since the ground is now warmer than the air around it, it automatically starts to rise. You've got that buoyancy. You have enough buoyancy to reach cloud condensation level, develop the cloud. You can now freely convect after this point. So convection cycles are a great trigger for inducing this rising motion and overcoming the stability of the atmosphere. And here's a great picture showing the effects of the convection cycle, clouds forming through convection. Now, the depth of the stable layer and the conditionally unstable atmosphere will determine how tall clouds will also grow. For instance, here at the surface, you have yourself a conditionally unstable atmosphere. But if you have a rather stable area up above that, then the cloud will not grow very much. Whereas if that stable layer keeps moving upwards, then the cloud can develop and form much taller clouds. Now, ideally, if you really want a very large cloud to produce some thunderstorms, the entire troposphere will be conditionally unstable or completely unstable. And then you have the stratosphere above you, which is stable. And that will cause the rising motion to stop. And when the rising motion stops, it has nowhere to go but out. And that's what gives the flat anvil top on thunderstorms. Topography is another great trigger for causing cloud formations. Air's moving along unsaturated. It's just minding its own business, really. But because it's a stable condition, it will not rise. But the mountain gets in the way, forces it to go up, and it will start to cool that way. And as it cools, it condenses, forms a cloud. All of a sudden, you get this free convection. It starts to rise up on its own. Now, here's a really interesting situation where topography plays a huge role. Let's say that you start off with an air temperature of 20 and a dew point of 12. The wind hits a mountain on what we call the windward side, and it will start to rise and cool at the dry adiabatic lapse rate, meaning the temperature drops down to 10 degrees Celsius. Well, the dew point drops at a rate of 2 degrees Celsius per kilometer, so it also becomes 10 degrees Celsius. You are now saturated. As it rises, it is now moist, so it cools at a rate of 6 degrees Celsius per kilometer, so it drops from 10 to 4 to -2. And as it's condensing, it's leaving water behind, so your dew point drops as well from 10 down to 4 down to -2, because the amount of water you have in the air has dropped significantly with condensation. Well, now let's go to the other side of the mountain, what we call the leeward side. that air starts to descend the other side. Well, as soon as it starts to descend, all the water was left behind. So as soon as it starts to warm up, it is now unsaturated. So it warms up at the dry adiabatic collapse rate. It goes from -2 to 8 to 18 to 28. Notice that you are now warmer than the 20 degrees where you started. And your dew point rises from -2 to 0 to 2 to 4 versus the 12 where we started before. So not only are we hotter now because we lifted at the moist adiabatic rate and descended at the dry adiabatic rate, so it's hotter, but it is now much, much drier because we left all the water on the other side. This produces what we call a rain shadow, a hot, dry region on the leeward side of mountains. Great example of this would be Death Valley. Death Valley is in a rain shadow from the Sierra Nevadas. Very hot, very dry due to this very nature we have in this picture. Here's another cool effect that can happen with topography. As the unsaturated air rises, it cools at the dry adiabatic collapse rate, and occasionally that air as it rises will actually condense and form a mountain wave cloud, also called a lenticular cloud. Here's a good example of a lenticular cloud that you might see due to the topography pushing air upwards, causing this region of condensation just on top of the mountain ridge. A third trigger is convergence, also known as low pressure. If you have a low pressure system, then it's pulling air in from all sides. Once that air reaches the center of the low pressure, that air is moving. There's nowhere else for it to go but up, and it pushes upwards. It creates lots of thunderstorms, which is why when you look at a weather map, it's always the low pressure systems that bring lots of thunderstorms. The fourth trigger is fronts. This is a very long region, a line of 1,500 kilometers or more. This we're not going to discuss much here because we have an entire chapter, chapter 8, which addresses fronts. And so here are the four basic types of triggers that we just went over: convection, topography, convergence or low pressure systems, and weather fronts. Notice the scale grows on each of these. Convection is the smallest scale. You're dealing with a handful of kilometers. Topography, mountain ranges are hundreds of kilometers. Low pressure systems reach an even larger area, and then weather fronts reach over 1,000 kilometers long. Through any of these four triggers, we can produce upward motion, and once we have upward motion, we can do cloud formation, and if the cloud formation is strong enough, we can get thunderstorms.